Let's have a look at the electron configuration of ions. So we're going to start this by picking something deep within the periodic table. Let's have a look at selenium 2-. This would be selenide. So we're going to write the electron configuration and draw the orbital box diagrams of Se2-. First of all, I would say go find where selenium would be. So it's in the 4p set. So the last term that I would normally be looking for would be a 4p term. So this is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p4 would be the neutral ground state electron configuration of selenium. Now, selenium 2- implies that somehow selenium has gained 2 additional electrons. Well, where should we put them? The p set of orbitals can hold 6 electrons, but in this case, as you can see from the arrow there, there's only 4 electrons present in it. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6 rather than 4p4. There's the electron configuration of selenide. To draw the orbital boxes, again, put the boxes in. Your orbital boxes, remember, this is just a pictorial version of an electron configuration. You need the same number of boxes as you have orbitals. They should have the same labels. So 1s, 2s, 2p, 3s, 3p, 4s, 3d. Okay, show all 5 orbitals for the d block. And finally 4p for this case. Right, all the other orbitals are present, but why bother to show them? So we're just going to stop drawing at 4p. So again, remember the up and down half arrows, each will represent an electron. So I put 2 in the 1s, 2 in the 2s, 6 in the 2p, 2 in the 3s, 6 in the 3p, 2 in the 4s, 10 in the 3d, and we'll load up the 4p here. So 1, 2, 3, 4 electrons. At this point, it's selenium. Add the 2 more electrons. This is now the orbital box diagram for Se2-. So what about a cation? Well, it's different. It's the other way around. The cation, remember, is going to lose electrons. So we're going to look at gallium. Gallium's right there. It's in the 4th row, element number 31. So it's 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p1. Okay. Gallium, 3 positive, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. This might cause you to question how I got that. Where did the 4s electrons go? We're going to have a look at the orbital box diagram here. Okay, I'm going to represent all of the orbitals that I've got in my diagram here, or in my electron configuration rather. So I'm going to fill in, represent everything that was on the screen in the first electron configuration. So this will be for gallium. So this is 1s, 2s, 2p, 3s, 3p, 4s, 3d, and 4p. So let's put the electrons in. Again, remember the up and down arrows each represent 1 electron. So 3p, 6 arrows, 6 electrons, 3p6. 4s2, 3d10, and I'm going to have 4p1. This would be gallium. Now, to make gallium 3 positive, I need to take out the 3 valence electrons in gallium. Valence electrons are found in the highest occupied principal energy level. So this is 4 rather than 3. So I'm actually going to remove the 3 electrons present in energy level 4. That leaves the 3d intact, 3 positive. This is saying that the electrons are going to be removed from the highest principal energy level first. So in this case, it's energy level 4. And that all the 4s and 4p electrons are removed before any 3d electrons are ever touched. This goes for any atom.